we saw that the definition of this m can be actually it reduces to a much simpler quantity if we assume that the axial temperature gradient is not a function of r. Now, next we see that if for example, if your u bar that you are considering is a slug profile. What was a slug profile? The slug profile is something like this, that your flow profile is something it's a profile like that. Okay, so where the laminar sublayer thickness is 1 to 2 orders, okay, smaller, okay, than the pipe radius, okay. So, it is a laminar sublayer thickness which is 1 or 2 orders smaller than the pipe radius. Okay. So, the slug profile means is essentially a constant velocity profile. If you recall, we did a problem in our laminar boundary layer internal flow where we did that the slug profile is given by a velocity u, right, which was kind of constant. We solved this earlier. So, when moment we say that it is a slug profile and therefore, it is constant, your m becomes of the value of 1, right, because u, okay, is essentially constant. Okay. The u is therefore essentially a constant over here, right. So, this laminar sublayer is very small, it is 1 or 2 orders smaller than the pipe radius. Okay. So, therefore, we can get away with this assumption that u bar is practically a constant in this case. So, moment that happens, okay, your q apparent double prime divided by q naught double prime becomes almost equal to 1 minus y over r naught. Okay, because the factor m is now basically equal to 1. So, in other words, what we can say is that the apparent heat flux okay, follows distribution okay, that is practically the same, okay, that is practically the same as one followed by the apparent shear stress. There is an important connotation that it follows basically the same thing as the shear stress, right, that you did earlier, right. So, so recognizing the definitions, of q apparent double prime and your tau apparent, okay, that yields gamma plus epsilon m divided by tau naught du bar, that is equal to Cp alpha plus epsilon h divided by minus q naught double prime dt bar. Okay. So, that is the expression that you get considering that both varies in a very similar way. Now, imagine that the pipe cross section is composed of two distinct regions. Okay. So, it is composed of two distinct regions. Okay. So, in the annular region close to the wall, so one region is y greater than 0 and less than some quantity y1, which is the annular region very close to the wall, okay. So, annular region very close to the wall, where in this particular region your gamma must be much greater than your epsilon m, okay, and alpha is much greater than your epsilon h. These are the two things that are valid in that particular region, right, in that region, okay. And therefore, there is a disc shaped okay, region in the center. So, this is close to the wall, very close to the wall. This is towards the center, okay, where your y plus is greater than y less than some r naught, okay, where you have your, in this particular region, your epsilon m is much greater than gamma, okay, and your epsilon h is much greater than alpha. So, this is the disc shaped region in the center. Got it? So, this is the disc shaped region at the center, this is the region which is very close to the wall. So, if you consider that it is composed of two distinct zones basically, okay. So, what we can do is that we can take this equation, let us call this A, integrate equation A, okay, integrate equation A from y equal to 0 to y equal to y1, okay. Okay. So, in this integration we are neglecting both alpha h as well as epsilon h and epsilon m are neglected. Both of these two terms are basically neglected, okay. So, therefore, if we do that, then what we will get is gamma u1 bar divided by tau naught is equal to Cp alpha divided by minus q naught double prime T1 bar minus T naught. Okay, let us try to see what these quantities are. So, U1 bar, okay, and your T1 bar basically are time averaged quantities, okay, at y equal to y1 bar, at y equal to y1, I am sorry. So, this is the first expression that you get when you basically integrate equation A from y equal to 0 to y equal to y1, where epsilon m and epsilon m h are actually neglected. Okay. So, therefore, these are the time averaged quantities of the same variables, okay, u and t at y equal to y1. Okay. So, this is the first expression that you get, okay, from the near wall integration. Now, okay, next up we integrate from y equal to y1 to y equal to y2 kind of. Okay. So, this is chosen. So, the y2 is chosen okay, such that T bar y2, that means the average temperature at y2, okay, is same as the mean temperature, which is T mean, basically the mean temperature. Okay, is equal to the mean temperature T, and U bar at y2, okay, is approximately the same as the mean velocity Remember the mean velocity that we did, u is the same as the mean velocity u. Okay. So, therefore, and here of course, we are neglecting the gamma and the alpha, right, because epsilon m is greater than both those quantities. So, when you integrate this, this becomes epsilon by tau naught u minus u1 bar is equal to Cp epsilon h divided by minus q naught double prime Tm or Tm bar, whatever you call it, T1, right. Okay. So, now what you can do is that from this is the second equation. Let me write down the first equation for the benefit. Tau naught u1 bar is equal to Cp alpha minus q naught double prime T1 bar minus T naught. So, these are the two expressions that we have. So, you eliminate T1 bar from these two equations. Okay. From these two equations we eliminate the T1 bar, and we use the definition of friction factor. Friction factor, as we know, is tau naught divided by half rho u bars, u square, right, and Stanton number definition. So, we use two non-dimensional numbers now, h by rho Cp into u. These were the definition of the two numbers, right. So, if you eliminate T1 from these two expressions, okay, so then basically what you can see is that you can get a more revised form of this equation. Okay. So, you can do it like this, say for example, from the first equation Tm minus T1, okay, Tm minus T1, you can do it like epsilon m by tau naught, okay, into q naught double prime divided by Cp epsilon h into u minus u1 bar. Okay. So, basically your T1 will be equal to Tm plus epsilon m by tau naught q naught double prime Cp epsilon h into u by u1. So, that will be from one expression. From the other expression you can get, so this I am just doing a rough scheme just to show you guys what happens. So, T1 minus T naught there is equal to gamma u1 bar by tau naught, okay, q naught double prime divided by Cp into alpha. So, T1 bar is equal to gamma, or basically T naught minus q naught double prime alpha Cp gamma u1 divided by tau naught. Okay. So, now it is very easy, you subtract one equation from the other, okay, and then apply the definition of Stanton number and the heat transfer and the definition of heat transfer coefficient written in terms of the mean temperature, as we already know. So, if you do that part of the math, you will get that your Stanton number will now come out to be f by 2 divided by Prandtl number T plus u1 by u Prandtl number minus Prandtl number T. Okay. So, this turbulent Prandtl number is basically, as we already know, this is epsilon by epsilon h, just in case you have forgotten it, right. Okay. So, that is the whole thing. Now, Hoffman's correlation, empirical once again, correlation yields u1 bar by u approximately equal to 1.5, Reynolds number d to the power of minus 1 by 8, Prandtl number to the power of minus 1 by 6, something like this. Okay. So, this now can be substituted if you want in this particular expression, and of course, we have the Colburn's Berne's empirical correlation. Okay, Colburn's empirical correlation, which actually tells you that Stanton number into Prandtl number 2/3 is basically equal to f by 2 rho, and it holds for Prandtl number greater than about 0.5. Okay. So, so what we can do is that now we can use different equations like 8.29. Of course, this is from the book, this is equation 8.29, but using this equation, let us call it B, okay, and an equation of f which is equal to something like 0.046, or it can be 0.078, depends on what we are doing. Okay. So, for higher Reynolds number, this is the expression. So, this is like C. Okay. So, combining these two expressions, you can find out Nusselt number, which is Hd by k, that will be roughly given as 0.023. Okay, Reynolds number to the power of 4 by 5 and Prandtl number to the power of 1/3. Okay, holds in 2 into 10 to the power of 4, Reynolds number is greater than this, and Reynolds number to the power of 6. That is where it kind of approximately holds. There may be lot of other correlations as well. Okay. So, one of them is given by Dittus and Beutler. So, there are tons of other correlations that you will find in different books, in different chapters, right. And so, in essence, okay, the Nusselt number is of this particular form, right. Okay. And you can read the book for varieties of other types of correlations that will exist in this particular case, right. Okay. So, this pretty much, so there are, read about the other correlations, read about other correlations. Okay. So, we have concentrated mostly on the few things in turbulence. One is of course that we have considered that using a simple Prandtl mixing length type of a model, which is basically a very ad hoc kind of an analogy. We were able to do some insights, right, about this law of the wall. We saw that very close to the wall there would be this laminar sublayer, then there will be a kind of a stable turbulent sublayer, and beyond that you have the outer region where turbulence is kind of very where you have the large eddies and all these things. Okay. So, there are of course you hear that there are lots of so how can this but this is all this analysis has got some ad hoc nature to it, that we were able to neglect some quantities in certain ranges, we were able to work out some other quantities in some other ranges. So, this might give you some picture of the wall heat transfer or the friction factor, and there are correlations which are very ad hoc, which assumes a velocity and temperature profile, but we were able to get some idea about how to handle these problems. What is however not really clear, that what are the other ways by which the same problem of turbulence can be handled. So, one is that, as we already know, that you can always have what we call a full DNS solution of the whole thing. That means you take the whole Navier-Stokes equation and you basically solve it. Okay. So, that would be one way of tackling the problem, that you take the whole Navier-Stokes equation. Other than that, if the Navier-Stokes equation is not possible, there are methodologies by which you can, there are large eddy simulations and things like that, which are more complicated, but there are like different types of model equations, like for example, you have heard the name of K-epsilon model. Okay. Similarly, there are Reynolds averaged 5 equation models and things like that. So, these are all ad hoc models in their own way, but they serve certain purposes somewhere, okay, especially in the outer region of the flow. Okay. So, one of these models is basically what we call the K-epsilon model. Okay. So, the K-epsilon model is one of the model. Okay. So, we already know that your epsilon m and epsilon h are unknown. right. This we already knew, okay, and mixing lengths were used to derive the same. Okay. So, they obviously lacks universality, it is not universal at all, which is quite obvious. Okay. Then the same model cannot serve, okay, cannot serve, okay, both inner and inner region, basically inner region and center line. It's impossible to do that. So, K epsilon model was basically a non-algebraic model. Basically, you devise two more equations. It is called a two equation model. One equation for K, one equation for epsilon, where K basically stands for the turbulent kinetic energy. Is basically, if you remember the matrix that we did, so this is basically what we call the turbulent kinetic energy. This is the turbulent kinetic energy. This is a non-algebraic model, two equation model in fact, okay, the K epsilon. Okay. So, it is basically the sum of the variance of the fluctuating velocity field. Okay. So, that is what is calculated as the turbulent kinetic energy, right. Okay. Next, I mean the turbulent kinetic energy is not all. So, if we look at the concept of eddy diffusivity, okay, we can write this as C mu k to the power of half into L, where L is basically an unknown length scale like a mean free path. Okay. So, in order to know epsilon m, okay, we need to have a knowledge of K and L basically, right. So, epsilon m is written in this particular way. This is the turbulent kinetic energy, this is some length scale which is akin to the Prandtl mixing length. Okay. So, this too needs to be solved if we have to solve for the, if we have to close, because we need to close epsilon m basically, right, in order to solve. That is what we did so far in the class, right. So, basically you use basically two equations to do this, right. Two equations are needed because your epsilon m is a function of two variables, the two new variables that you have included, you have suddenly brought out. Okay. So, naturally in order to solve this equation you just need two more additional equations, right, to solve that. Okay. So, in any control volume approach, normally in a full fledged turbulence course you would actually solve for this equation. So, the convection of K, okay, is defined as dk by dt, okay. A diffusion of K by, so basically you write transport equations, that is all that you are doing, okay. Sigma K dk by dy, okay. So, here of course the assumption is that epsilon m is much greater than gamma, okay. K diffusion is therefore is due to eddy viscosity only. Okay. So, this is basically a constant. Okay. So, these two should be clear, one is basically the advection and one is basically the diffusion of K, right. So, therefore, there could be a rate of production also of K, which is given as epsilon m. It is a transport equation. So, you should have all these kind of equations over here, y and du bar by dy, right. So, this is eddy shear stress, and this is some kind of an average velocity gradient. So, this is the production term, okay. Okay, or in other words, this is further written as, this entire thing is subsequently written as epsilon m du bar by dy square, right, which in other words I am writing it here, C mu k half L du bar by dy whole square, so something like that, okay. Now, of course, there is now, so there is a advection, a convection, there is a diffusion, there is a production. Now, there is only other thing that is remaining is dissipation. There should be a dissipation of K as well. Now, we will see in the next class how that dissipation equation is actually written, okay, because once we are able to write the dissipation equation, then we can write the full transport equation of K and then see how that equation can be solved, okay. Similarly, our equation can be written for the L also, okay, equivalent of L, that we will do in the next class. To just give you an idea that how the same turbulence problem, that same eddy viscosity and other things can be solved, okay, in a little bit more complex way, okay, by using two more equations. Not necessarily that this is any better, okay, it just gives you a little bit more freedom in juggling the quantities, okay. Thank you.